Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Good. Okay, I think we can start now. Okay, it's good to have Ola Svensson from EPFL back here. And today he's going to tell us about the Matroid Secretary Problem and some algorithms for it.
Thanks. I don't know, you saw my talk. I don't know, Sasha might have missed it. Sure. So it's joint work with Moran Feldman, who's also at EPFL, and Rico Zenklusen, who's at ETHZ in Zurich. So it's the sister institute of EPFL. So it will be about the Matroid Secretary Problem, which is a generalization of a classical problem, so classic secretary problem. So let me start by introducing that, and then I will argue why we're interested in the generalization and what the generalization is. So to make it a little bit more interesting, so let's say instead of secretaries, let's say jobs. You know, everybody applies for jobs once in a while, and we want to get the best strategy to get the best job offer. Okay. So you have applied for n jobs. And the goal is to somehow devise the best strategy to select the best job offer you get. So you know how many jobs you have applied for, normally, okay? So you know n in advance, and now you want to select a strategy that so that you select the best offer. Okay? So what's the rules of the game? You assume that the offers will arrive in a random order, okay? So you assume, that makes sense. You don't think that employers will unite against you to make your life miserable. And then you also assume that you can, when you see an offer, you disagree. Maybe. I don't know. I have good experiences. You might have bad experiences. And then you also assume that when you get an offer, you can actually assign a value to it. Okay? Some value, and you can compare it to what you already saw. What makes it, you know, of course, the optimal strategy is to wait for all the offers, take the best one. But what makes it interesting is that you have to somehow make your decision immediately. Okay? So when an offer arrives, you have to immediately decide whether to accept it or not. Okay? Your decision stays there. So when you accept one offer, the game ends. Okay, so here's an example. Mona Lisa applies for job, random order. So the first offer might be TU. So that's, I was thinking if I want to record this. So first offer is TU Berlin, maybe, you know, value 7. So I've been nice. But, you know, first offer you can expect something better, so you reject. And then maybe you get Princeton, 8.1, will also reject. Then Walmart, you're surprised. So it's a reject. So actually, when I gave the presentation, some people were surprised that I didn't like Walmart. I don't know. In Europe, it has. Okay, anyway. And then I'm nice, you know, Microsoft Research 8.2. So you maybe accept. So what's the best strategy? You know, probably.
To wait till Microsoft Research.
No. You wait till EPFL. But you know, in general, what's an optimal strategy? Or not an optimal, let's say just a reasonable strategy. Use all. Yeah, okay, yeah. So you basically, there are many optimal strategies, but the one that makes intuitive sense is you have two phases: a sample phase, see what you can expect, right? You don't know what to expect in the beginning, so you sample a fraction of the input to see where you are in the market, and then based on what you have seen in the sample phase, you make a selection. So in the single secretary problem, what you will do is to, you know, just look in the sample phase. You reject everything irrespective of the value, but you remember, in particular, you remember the best solution in the sample. Okay? So the optimal selection in the sample will be 7. And now remember that you're interested in selecting the best possible offer. So the only thing that it makes sense to accept is something that is greater than 7, right? So what we will do is to accept the first thing that is greater than 7. So if it's less than 7, 6.5, we reject. 2, reject. If it's 8, great, we accept. Okay. And it's easy to see that this is a constant, okay? So suppose we observe, instead of observing, I can write here, so instead of observing 1 over e, we observe 1 over 2 fraction, okay? So now I claim that the probability of selecting the best of is at least 1/4. Why? Because we are guaranteed to select the best of with the second best in the sample phase. That happens with probability 1/2. And the best is in the second half, which happens with probability 1/2. Okay, so that's probability 1/4. You multiply. Okay, they're not almost independent. And 1 over e comes from, you can it's a little bit more complicated, but you can see like, even if we take the third best here, there is some probability to select the best one, if that comes before the second best and so on. But anyway, 1 over e, it's not too complicated. What is more surprising is maybe that it's also the best, okay? So this was proved in the 60s by Duncan, 63. So it's a quite long history, and it's studied independently in the West and the East. So that, okay. Maybe you, this guy, maybe you can explain to me after the talk. This guy always pops up at different places of my slides when I use the pen. Since you're here, maybe you know how to get this out of my slides. Yes. So we are interested in a more generalized version. Luckily, we are not the only ones, and we are not the ones that proposed more general versions. So this is because of online mechanism design, and Kleinberg, I think, was the first one to look at more general problem. And then it was Babayev et al. In 2007 that defined the Matroid Secretary Problem. So why are they interested in the Secretary Problem? Well, there is an immediate connection if you think not of secretaries, instead you think of bidders arriving online. Okay, so you have customers arriving online, and you are selling goods. But you have a limited amount of goods you can sell to the bidders, and you have to immediately decide if you're going to sell it to the customer or not. Okay? So think of the single secretary problem. There you have one good you want to sell. Okay, I have a car. And now people contact me online in some random order telling me their bids. And if I sell the car, I sold it. But I can also reject the offer, but then the guy might buy some other car from some other provider. Okay, so that's the single secretary problem. Now you can imagine generalizations where you have many cars or so on. And that's the immediate generalization that Kleinberg considered in 2005. So instead of only having one good you want to sell, you have k out of k goods. And you have n guys coming in a random order making bids. Okay, so k identical goods. And here, in this generalization, the goal is to select the k secretaries of the maximum total weight. So each value. So you're not so interested in only selecting the best, but you want the total weight. Okay? So if I have 1 out of n, I can do 1 over e in expectation of the total of the optimal offline weight. That's the best I can do. What do you think is k out of n? You think it's easier or harder? Intuitively. You think it's an easier problem with k out of n than 1 out of n to get a good weight compared to the optimum offline?
It can be 1, so...
Okay, but when k grows, let's say k is 100.
It's very easy because you do it here.
It should be easier. Why? Intuitively it should be easier because you know one decision is not so important. So you're allowed to do some mistakes, and that's the case. So his result says that in this case, we can do something like 1 minus some O of 1 over square root of k. Okay? So when k goes big, you can actually go arbitrarily close. Or when k goes to infinity, you will get arbitrarily close to offline optimum. Another, so this is one generalization. Maybe a generalization that is a little bit more interesting that actually captured my interest in this problem is the following. So suppose you're a provider, okay, so you have some server, maybe Netflix, whatever, and you have a network then of your network cables, and they have certain capacity. So the capacity is the blue numbers on the edges. And now you have some clients that will arrive in a random order and will bid to be guaranteed a unit connection to the server. Okay? So suppose this blue guy I'm saying I'm willing to pay 4 to get the guaranteed unit bandwidth to the server. Okay? So I say, okay, I will provide that to you and you pay me 4 units. Okay, so this would be one way of guaranteeing, but it's not a unique path, right? I could also give him that path to the server. And it's not important which path I give him. I can change it later on, as I always guarantee him to 1 unit of bandwidth to the server. Okay. Now the second guy can arrive. I bid 7. I say, OK, great, I take you as well. So look, now to accept him, I have to change the path of the red guy. But I can still accept him. Because, you know, here, somehow, there is no way to connect the blue guy without changing the path of the red guy. Now this guy comes 6. Well, I already used quite a lot of my capacity, so let's reject him. 5 reject, 9 accept. Okay, and now I'm somehow, this is the total amount of customers I can accept because my network supports at most 3 customers. So 10, even though it's more than 9, I have to reject. So the question is, how well can you do here compared to the optimum offline? So optimum offline is easy to solve in polynomial time. Okay, that's just a greedy algorithm. And that's actually an open problem. We don't know. So it's a nice open problem is if there is a constant competitive algorithm for this problem. So constant competitive means that the online algorithm should at least do a constant fraction compared to the optimum offline. Okay, so an online algorithm is C competitive if it gets a C fraction of the optimum offline.
Sorry, for offline, you said greedy will work to do it?
Yeah, I mean greedy, it's a matroid. So so you will take 10. Then I don't know if you can take 9 or not, but you take the next one that you can take. Okay.
Is it important to assume that their offers are bounded between 2 constants?
No,
or?
no. Actually, we will not assume that. If you assume that, maybe you can do better. Okay, so then, if you assume that, then you can do something that is, if they're integers between some numbers, then you can do log of the range or something like that, by just rounding.
So a priori, it could be that one guy dominates the sum of everyone.
Exactly.
You have no idea that this is the case.
And that's why you cannot do better than 1 over e for the 1 out of n in the weight version.
Yeah.
Yes.
Yeah.
So yeah, like I guess that's the ordinal version maybe, yeah, where
Yes.
I tell you whether I'm better than which in the order where I land up in my value.
Yeah.
You don't put
I think our algorithms would work for that case. I think so. I'm not 100. They are easier to explain when you have weights. But yes, you can also assume that you can only compare the items. That's somehow a harder version, right? But I don't know if it's really harder, but it's definitely not easy. Yeah, so this is this is actually, so both the case I told you were a special case of matroid, so this is called a gamoid. So it's a special kind of matroid, and that's so these 2 examples are nice, and that's what's nice with the Matroid Secretary Problem. So somehow it captures many nice applications. And what is the Matroid Secretary Problem? Well, it's a secretary problem where we have a matrix constraint on the elements to be selected. Okay? So one matrix constraint would be that you can select k out of n secretaries. Another matrix constraint is that I can select the clients that I can provide unit bandwidth to the server. That's called a gamoid. Okay, if you don't know what the matroid is, you're having a problem. No, I'm kidding. I will define it on the next slides. But also, if you don't understand, so it takes a couple of presentations until you realize what the matroid is. So I will do all my examples on graphs. So the only thing we will worry about is to select edges that are acyclic. Okay, so that I hope everybody have seen. Then yes. So to understand what I'm going to say afterwards, you only need to know what an acyclic graph is. So why study MSP? So yes, as I said, it captures many natural settings. And then basically matrices are defined so as the naive greedy algorithm works. So that the definition of matrix is that Kruskal's algorithm should work. Okay? Guarantees that this algorithm. So they have a very nice structure. So the hope is that you somehow found the best problem that captures many settings, but at the same time you have very good online algorithms. So here we are pretty confident. The problem is in the second part, we don't really know if the structure is enough to get very good algorithms. And that's what we are trying to solve and try to understand. So let me, before then explaining what we know about the algorithms for these cases, let me define a little bit what the matrices are. And as I said, so matrix formalized problem can solve by greedy Kruskal's algorithm. So if we are looking at graphs, okay, so here we have a graph, and now we are looking at the graphic matrix on this graph. That is the graph correspond to think about the graph correspond to forests. Okay, so what the elements of this matrix will be the set of edges of the graph. Okay, now all possible feasible solutions will be all forests. Okay, so that's the independent sets in the matrix. Okay, so all the subset of edges that are cyclic. Okay, so that is a graphic matroid. So what kind of constraints do we use when we prove that the greedy works? I think it's exactly what you need to make it work. Is well, first, yes, so we have a ground set, that's the edges in the graphic, and then we have a subset of all the sets of this ground set that are our independent sets. So what are the constraints? So first constraint is kind of simple. That says that if we have an acyclic graph, so this says if we have a set of edges that are acyclic in the graph method, then if I drop an edge, it should be acyclic again. Okay, so it's downward monotone. The second thing says that if I have two acyclic graphs, set of edges, I and j, and I is of a bigger cardinality than j, then there must be an edge in I that I can add to j and it's still acyclic. Then there exists an edge in I that is not in j that I can add to j and it's still acyclic. Why is this? Think about it. So if you have I, many edges that are acyclic, then you have few components of the graph, right? So there must be more components in j. So this means that there must be one edge in I that connects two of the components in j. And this graph, I mean, adding that edge will be acyclic. Okay. So that's what a matroid is. Not so intuitive if you see it the first time, but after a while, it gets intuitive. When you get used to the definition, it gets intuitive. Another very natural example of a matroid is, yeah, right. Okay, one question one has when one sees this, how can you have this? This looks like a hard encoding, okay. So you have maybe independent sets like exponentially many. How can you encode a matroid? And what people assume is that they have an oracle that returns if a set is independent or not. Okay, so think of the graph case. You have exponentially many subset of edges, but you can efficiently check whether one set is acyclic or not. Okay, so another example is a linear matroid. Here you have some dimension m, and your set E is a subset of vectors. Okay, finite. The universe is a finite set of vectors, and all the independent sets are those subset of vectors that are linearly independent. Okay, let's now check that the axioms are satisfied. So in the first case, suppose I have like 3 independent vectors. If I drop one, the 2 guys that remain are independent. And the second constraint, suppose I have 3 independent vectors in I and 2 in j. Well, then I can add one of them to I to make it bigger. Okay? Yeah?
Gamma is a subset of the linear?
I don't know.
Yes.
Yeah. So a constant factor approximation is not known for,
No.
of course, for linear matrices.
Actually, if you can get the constant for linear, I will be surprised if you. Okay, I don't know. Maybe there are probably there are some weird properties known for linear matrices, not known for general matrices, but I don't know about them.
Linear matrices are almost complete.
Yeah, but a typical matroid is not a linear matroid.
Yeah, okay. But, yeah.
Sure, but
Anyway, so let's look at what is known. So as we have talked, there's a lot of special cases. So actually for the graphic matroid, there is a competitive ratio of 2e. So you only lose a factor of 2 compared to the single secretary. Something called transversal matroid 8. Co-graphic matroid. Don't ask me what all these matrices are because I don't know. But K-sparse, this is K-sparse linear matroid, okay? So what is a K-sparse linear matroid? Well, I would guess that it's a linear matroid where the vectors have only K non-zeros, okay? So here you see that this is not really constant when you have a higher dimension, okay? So this is still open for linear matroid, that's true. Laminar matroid is a good regular matroid. You see where we're getting at. You can look at all your matrices, favorite matrices, so almost except linear and gammoid. I don't know if you know any other where we don't have a constant. And this then, I think it makes, so they made a kind of a bold I mean, this Babayev et al. That defined the problem, they made a pretty bold conjecture probably in 2007, but now it looks like it's, I believe in it. So what they proved is that there exists a competitive algorithm for the problem in its generality.
One is actually a special case of 4, right? Just
Sorry?
the graphic matroid is a special case of the k-sparse.
Yes.
Yeah.
Yes.
Yeah.
It's a 2 sparse. Right. So this generalizes that. Good.
Although I'm not sure how many of these results are satisfactory in the sense that they assume what your matroid is. So again, so again,
Yeah. Okay. So this kind of detail. So there is different versions of the Matroid Secretary Problem where you assume if you actually know your universe in advance and that you can query the independence oracle of the whole universe before seeing the elements, or if you only get to know where the elements are in the matrix when they arrive. Okay. Because so that's kind of a detail. Yeah. I think if you can solve the Matroid Secretary Problem, even if you know the whole matrix in advance, but not the value of the elements, that would be great. So we don't know that. Yeah, so the open conjecture is if there's a constant, and actually what is consistent with our knowledge today is that there could be an E-competitive algorithm, the same as for single secretary. So that would be nice. And not completely out of, completely crazy to say that. So there is another problem that is related called profit inequalities. And there was an old result in statistics or probabilities that gave a 2. Okay? And it was shown that 2 is also the right answer for any matroid. So somehow the nice thing with matroids is that, they can capture many settings, but things don't get messier. Well, they get messier because we haven't solved, but hopefully they don't get too messy.
So you think of k times e as a constant?
No. For a fixed k, it's a constant. So we haven't solved this yet. Yeah, so it's true. So so I enumerated and said that they were constants. Maybe this is an outsider. Yes. So that's true. So what do we know about the general case? So there is a very simple Logrank competitive algorithm that I will explain today, actually. So it's by Babayev et al. From 2007. And then there is a more complex squared Logrank competitive by Shekabat and Lachish in 2012. And then there's a loglog, recent loglog rank for Lachish. Okay? So what one can say here is that it's been like very non-trivial to improve Logrank. Okay? So they're very complex algorithms. And you can also, so one indication that the last time is fairly complex is it's the hidden constant in the big O notation is at least 2 to the power of 2 to the power of 32. Okay? So why is the hidden constant so large? Because the algorithms also follow this that you first sample and then you select. So you want to have a large constant because you want to get a lot of information out of your sample. And you want this information to be reliable, so you want to have concentration. And to get concentration, well, it's good to have many elements. So what we will do is to get a similar ratio, but we will use less information from the sample, and we have a modest constant. So a simple 3000 log rank. And it's quite simple. So it's very simple relatively to the previous algorithms, but it's not so simple. I give you the ideas, but I think maybe you will not understand the whole. Hopefully you will understand, but maybe not.
Are you going to tell us more or less what the rank of the rank is?
Yeah. Sorry. So good question. What is the rank? That's the maximum number of elements you can select. The largest set of an independent set. So in a
That's okay.
Yeah.
I mean.
So in the linear matrix, it corresponds to normal rank. And for graphic matrix, usually it's n-1 if the graph is connected. I mean, it's a spanning tree. Yeah. Yeah, so basically the general technique here is that you start with a complex problem, and basically we will use a sample and so on to reduce it to a set of very simple problems where we run the naive algorithm. Okay? And we will see why this works. So one thing we could notice when I introduced the single secretary problem was that the only place where we really used, at least for the 1/4 argument, the only place where we used the randomness was to get the sample. After we got the sample, the order could be adversarial in the selection phase. Not to get 1/e, but to get 1/4, it doesn't matter if, as long as I can get 50% of the elements at random, the adversary can give me the remaining as he wants. And this is the same case in this algorithm, okay? So the only place where we use the randomness is to be able to access 50% of the elements at random. Then the adversary can give the elements as he wants. I don't know if it has, I think it has some applications, but I don't know. Okay, so let's look at the algorithm. As I promised, we will look at it as in the graphic method, okay? So let's first, so I will give 3 algorithms. So the first one is the naive approach, which is like the first thing you would try if you look at the single secretary algorithm. How would it work here? And then I will give you the Logrank, and then we will see the loglog. So what about the naive approach? So what did we do in the single secretary? We sampled 50%, we remembered the best solution, we took anything that improved on that solution. Okay? Now we do the same thing. So we sample a set by including each element with probability 0.5. Okay, that's almost the same thing as taking the first 50%. Okay, so suppose this is the optimum solution in the sample. Remember, we remembered 7, the best secretary in the sample. Now we remember the best forest in the sample, the maximum weight forest in the sample. Okay, and now when an element arrives, we should only take it if it was part of the best solution with respect to the sample. So 2 would not be part of an optimal forest, right, with respect to the sample, because it's spanned by heavier weight elements. Okay? It will create a cycle where all the other elements of heavier weight. So it will not be part of a maximum weight forest, so we don't take it. Okay? So improving if not spanned by heavy edges. Yeah, I haven't defined span. Span means that they create a cycle with you. 4. We take. 4 is better than 3. It will be part of the optimum offline solution. Okay. 7, we should take, right? Because it's not spanned by heavier elements. 2, should we take it? Yes. Yes, because it's better than 1. Okay. 11, we would like really to take, but now we cannot take it. Okay, so that's why online is not so good here. Okay, why we lose. So this would be our solution. It will be 4 plus 7 plus 2, which is 13. Okay, so why is this not good? So we call it the hat for some reason. It looks like a hat. So you have some really expensive edge here that you really want to take. Then you have tons of vertices. Okay. Up here of very light edges. So basically, optimal solution is equal to the weight of the heavy edge. Okay. Let's now run this algorithm on that. So you get some sample. Well, let's assume that the heavy edge is not part of the sample, because if it's part of the sample, you will not be able to gather anything in any case. So now we are extremely likely to see many of these edges, right, before this guy comes. Remember that they arrive in a random order, okay? Because there are so many of these edges. Let's see, 1 minute. Okay. So, oops. So maybe this one arrives. Well, it looks like it should be part of the optimal offline solution because it's not even spanned by any edges in the sample. So let's take it. Then this guy comes, same thing, it looks like it should be part. Then this guy comes. Again, we should take it, right? And we're extremely likely to see some situation where 2 of these arrives before this guy arrives. So this will prevent us from taking the fat edge when it comes. And we are out of the blue, okay? Did that make sense? Okay. So now you can argue, of course, that this is a special case. There's only one element that is important, so let's run the single secretary argument, which would work for the hat. But we have this generalized hat, where you have first a very heavy element, then you have medium heavy elements, and then on these you have another hat and so on. And here you can actually see that you have you get a log relationship, basically, okay? And that's why we will see where you have a log there is a simple log algorithm. So basically here you have the heaviest guy, then you have some factor lighter elements, then some factor of that lighter elements, and so on. Okay. So that's their algorithm. So it's a weight class algorithm. So that's why I have this. You just group your elements according to weight. You take one weight class and run it on that. Okay. So let me see. So this is okay. So we classify the elements according to weight. So here I make some assumptions that you can believe or not believe, but it's easy. So we know, well, approximately, but assume for presentation that we know exactly the number of elements, the rank of a matroid. This you can get from the sample easily, okay? So we know the number of elements up we take, and we also know the highest weight of an element. Okay? This looks dangerous, right? Because in the hat example, you would like to take the highest weight. But the solution to this is with some constant probability run the single secretary problem, and then otherwise run your complicated algorithm. Okay, so if we know this, now I claim that we can change it into Logrank many weight classes. Okay, why? Well, first of all, we also assume, let's say that by scaling, the heaviest weight is equal to the rank. Okay, by scaling. Now you just round each weight to the nearest multiple of 2. This will cost you a factor of 2. Okay? How many multiples factor between 1 and the rank are there? There is log r. Okay? And that's what they do. So weight class I is Ci is the one with the weight between 2i minus 1 and 2i. Okay, so you have weight class 1 is between 1, 2, 2, 4, 4, and then you have, the last weight class contains all the elements with weight between r over 2 and r. Of course, why don't I have to care about the elements with weight over here? Okay, but remember that the maximum number of elements we can take is r, and there exists one of weight r. So this means that even if I take all of the elements down here, they are not very important for the optimal value. So that's why I can forget about really lightweight elements. So I only have log r many different. After doing this rounding, you should think of it, elements can only have log r distinct weights. So we have only log r distinct weights. Okay, so log r many weight classes. Yeah, by losing a factor of 2, we can assume all elements have the same weight. So how is now a log r rank competitive algorithm? How would you do? So now, okay, one thing. So now it doesn't matter. All the elements are in a class is indistinguishable with respect to weight, right? They have exactly the same weight. So now, if you want to select the maximum set of linearly independent vectors, you can just add them greedily, right? It doesn't matter in which order you add things. You will always get full dimensional. So that's the same thing here. Just select one weight class at random, and now just greedily add things from that weight class. Okay. And that's what we're going to do. Okay. Yeah, okay. So what is their argument? Sample S by including each element with weight 0.5. Then they use this sample to calculate the rank and the max weight. Okay, so that's the only thing they use from the sample, only to calculate the rank and the max weight. And then they form the weight classes. And then they select one of the Logrank weight class at random. And then they greedily select elements from this weight class. Okay, so here they use the matrix property that it's not important in which order you select the elements of a weight class. You will always get the maximum set of independent elements of that weight class. So in an example here, if we selected a blue weight class, we would take all the blue guys when they arrive, but we would not take anything else. Okay, and this is exactly 1 over log of the optimum. Okay. Yes, so it's a log rank competitive. Well, consider opt the random weight class contributes opt over log rank to the optimum. We selected that, and okay, we lose a factor of 2 because of the sample. Otherwise, we get it. Okay. So yeah, I don't know if I confused you. Okay. So think about it. So what we're using is like in a spanning tree case. Suppose you're looking for a connect in the graph, right? Now, if you get edges coming to you, then you can just take edges as long as they don't form a cycle. It doesn't matter, you know. You should always take an edge that decreases the number of connected components in a matroid. So, yeah. So, okay, even if you didn't understand, it's not the whole deal. So, but what you should understand is that we used extremely little information from the sample. Basically, we use it to calculate the rank and the maximum weight class. And now, but on the other hand, if we looked at the example of the generalized hat, it really told us that we wanted to protect heavy elements from light elements. The problem was that we had one really valuable guy, right? And then these light guys came and messed up our life. And that's what our algorithm will do. So we will have two steps that I will explain later on. And the first step is really this. It's just that it will try to protect heavy elements from being messed up from light elements. So first we sample 50%. This might be our sample. And yeah, the first step is to protect heavy elements from light elements. And this second step is a little bit technical condition. It is actually to decompose a problem to independent subproblems. Let's not worry about that at the moment. Okay? So let me explain by example. Suppose we have this sample. So the green edges are the heaviest ones that we saw in the sample. So the blue ones are the second heaviest. The red is the third heaviest. And these violet guys here, they are the lightest. Okay? Now suppose a blue guy arrives. The first check here, is that we should check that he should not be spanned of heavy elements. Okay? What do I mean by that? We should check that the green guys do not create a cycle of him, because the only guys that are heavier than him is the green guys. So we should check that the green guys do not contain him in the span. Because if he is contained by the green guys in the span, then for sure the optimum will never take him, right? Because they would first select the green guys. So that's a sanity check. Now the second condition is because we want to be able to decompose a problem to independent matrices. But what we check to do that is that actually this edge is contained in a cycle if I look at the slightly lighter element than himself and all the other elements. Okay, so I will look at the red elements plus the blue elements plus the green elements, and I will check, do all these elements create a cycle with myself? And they do in this case. Okay. So that's the second condition. So it's spanned by elements in S of just smaller or higher weight. Okay? And in this case, it is spanned, right? Because this creates a cycle. Okay? So we pick it. Okay. So that's the two conditions. The first one is natural. The second one is a little bit weird. And it is just because we want the problems to be independent. So the hat example, how would it work out? This guy, he's spanned by, he's not spanned by heavier elements, right? Because right now I only saw the blue guys. They have all the same weight. So he's fine with the condition 1. Is he fine with condition 2? Yes. He's spanned by actually the same weight. I didn't even have to use lighter elements. Okay? So I take him. Then this guy arrives. He's fine with condition 1. He doesn't span by heavier elements, but he's not fine with condition 2. Because there is no cycle, even if I look at all the edges containing him. So I should not take him. Okay? And this is good news, because if this was exactly the dangerous problem, right, that I had 2 edges like that I took. But now I will never be able to take 2 edges like that, because I need one of them to have it in the cycle. Okay? Like I had over here. Here I had 2 edges. So this one was part of my cycle, and therefore I could pick that one because they created a cycle. So I will never pick that one. And therefore, I will never create the case when I took 2 guys. So this one is part I can always take. Actually, so it's a constant competitive ratio for the generalized hat, which is good news. As far as it's explained as follows. So the slightly smaller means that I look at one weight class before me. So how many have you seen matrix before? Nobody has seen matrix before except Mohit. Yeah, okay. So one can formulate this as this algorithm formulated in Matroid notation is the following. So we define one Matroid for each weight class, okay? So how is the Matroid defined? So let's look at Matroid M1. Well, M1 is not so interesting, so let's look at M3. Well, M3. Okay, so M3. So what does this mean? Well, we contract all the elements that are heavier than the third weight class. That's the blue big sets. And then we induce, and it should be in the span of the slightly lighter elements. Okay, so this is these red edges here. They are a span of slightly smaller elements. And this is the Matroid. And the reason that there's independent subproblems is because you contract what is in the span of the previous one, and they will be nicely formed like an onion. Okay. so that was just a side remark for those that knows matrices. Okay. But let's now analyze this algorithm. And to analyze it, it's really intuitive to think about it as in the first case that we have these two cases that we take an element if it's not spanned by heavier, but it's spanned by slightly smaller. Okay. So basically, by definition, you will get the following claims. So the algorithm picks an element E with probability at least the probability of being spanned of elements with just smaller weight and higher, minus the probability of being spanned by the same or higher weight. This basically by definition, because we take an element, if it's not spanned by heavier guys, including my own weight class, the guys I took of my own weight class, and it should be spanned by smaller weight. Okay. They might be dependent, that's why I don't have a price. I have the unibars, so I have just smaller weight and higher, minus same or higher weight. Okay. This probability has to be larger, right? It contains more elements, it's just smaller weight. So the probability is over the sample, okay? Tell me.
But like when you also, sometimes you don't pick it because it forms a cycle with whatever you pick. So
Yeah, so that's why I have the same or higher. The same, so I will only do it for every second weight. I was lying a little bit. I will only pick every second weight class, and that weight class I will check that it's not spanned by the same elements that I took. Otherwise, it would be only higher here.
Okay, so there's sample involved over here, which I don't see. Okay, so when you say probability, this is of course probability over the sample.
Okay, good.
Span of elements, which elements?
Well, elements in the sample.
In the sample.
Of smaller weight and higher.
Okay.
Minus probability of being spanned by elements in a sample of higher weight, and those that you picked of the same weight. But notice that we took 50% of the elements, and in the worst case, we will take all the remaining 50% of the same weight before I arrived. And this has the same distribution. So that's why we took 50%. Okay. So it's just so you can think of it as the probability of the sample to be spanned of the smaller weight and higher minus the same or higher weight. Okay. And let's now understand, we want this to be high, right? We want an element to be picked with high probability. So let's understand why this is good for the hat example. So let's look at an element, and suppose it's part of weight class I. Okay? So here the graph says this is the probability that is spanned if I only look at things that are of the same weight or higher. And here is if I look at slightly lighter elements and higher. So what happens in the hat example? When I look at my same weight and higher weight, it's very unlikely to be spanned. But then I look at one weight class, that's the hat I hang. Then I'm extremely likely to be spanned. So basically it looks like follows. And that's why we get very likely to pick elements in the hat, because they're extremely likely to be spanned once I go for one lighter set of elements. Okay. Unfortunately, this is the general situation, that there is no such big. That's why we don't get a constant. There is not these nice jumps. Okay? And now we have log and weight class here, and now we are stuck. So now we don't know how much information we can get as a sample. So now the last part in the algorithm is actually to randomly group these weight classes. And now you have log many classes, and we will do geometric grouping again. Okay, so here it's a little bit hard to understand, but so again we will group these together in a random way. And first we will decide how many weight classes we will group together. And we will do this geometrically. So either we group one weight class together, that's to keep the original weight classes, or we take 2 together, or 4 together, or 8 together. So it will be log rank many choices. And then you also have to take a random shift based on the size of your weight grouping. Okay, so this is a pictorial view. So now we selected the size of our bucketing, and then I will do a random shift. Okay, and now the probability of picking my element will exactly be this, the probability of being spanned here minus the probability of being spanned there. Okay, so it's 0.2 minus 0.1. If I was luckier, it would be 0.3 minus 0.1 and 0.8 minus 0.1. So. Okay, and what one can show is that this method will give you exactly log rank. So the intuition is that now there is log rank many choices, because first we had log rank many weight classes. Now we had log of that many different bucketings. So I think the main message was that I think the Logrank competitive algorithm only used rank of Matroid. So we used the Matroid structure, well, the protection of higher weight elements. And this allows us to currently get the Logrank competitive algorithm. So let me say, what is the difference between, as I understand it, the difference between Lachish and our approach is that we did this geometric grouping, right? And actually this random choice is independent of the sample. What he will do is take the sample, and I think he will then engineer the best possible decomposition. And for that, you need very high certainty to argue that the best possible decomposition for the sample is also good for the remaining part. So that gets hairy. I think so. But so that gets very hairy with very big hidden constants. But he has the advantage that he claims that his algorithm selects log rank with high probability. Our algorithm selects log rank fraction in expectation. So what is my belief? Actually, I believe that there is a decomposition that guarantees a constant fraction. So we have some, if we could, so we don't really know what kind of information of the sample we get out. So we have some sufficient conditions to actually write down a decomposition. But we don't know if the sample actually gives us enough confidence for these properties that we need. You can ask me later on. OK, so thank you.
Questions?
So do you have an example where the median of what you select is much smaller than 1 over log the rank of the optimum?
Yes.
Basically, that happens when you have to pick one particular size of the bucket.
Yeah. I mean, one trivial example in our case, I think, is to have the hat example. I think, because there you have 2 weight classes, but our algorithm will never look at that you only have 2 weight classes. And now with huge probability, you will group them together, and then you take nothing. Yeah. You don't take the heaviest guys.
So basically, you get 1 with probability 1 over log.
In that case, yes. So when you have this case, then you get. And I think what he will try to understand what case you are in.
So your algorithm uses more randomness, huh? Like your own randomness, I believe. Huh?
Yeah. So it's over expectation.
Okay. And the other one you said doesn't use that, or also? Or?
I don't know, but I know that he's engineering how the layers decomposition will look.
Okay. But like the natural question would be: is that necessary to use your own randomness?
Probably not, but I don't know. I mean, yeah, it sounds weird that you need to use your own randomness, but I don't know.
So where do you lose your constants?
Yeah, that was I don't really know. So there is some losing constant to reduce that you know the maximum weight and the rank, because you have to run to assume that you know the maximum weight. You have to run the single secretary algorithm with some constant. Then I don't know. 3,000 is a conservative estimate. It's not what is in paper. Within the paper, there is some plus. So I thought it would be easier with writing 3,000.
Let's thank Ola again.